My name is Joseph Wunderlich. I'm a professor of engineering, architecture, and computer science. IBM research before that, Children's Hospital robotics before that, built high-tech office parks before that. I'm 60 years old and done a mixture of high-tech and architecture, mostly high-tech. This is a lecture on building a simple PC. Nothing fancy, but just the basics of building a PC. It's in two parts, and they're PowerPoints with embedded audio that I'm just going to play and then comment, maybe stop them as they're going, and add some at the end. This lecture is on designing and building a personal computer. My name is Joseph T. Wunderlich. I'm a professor of computer engineering at Elizabethtown College. Firstly, we want to ask ourselves, should we build one ourselves or buy it? Here is some of the positives of either choice. And this is very much a matter of opinion in some cases, and you're welcome to argue it either way on exams. Just support your belief in which way to do it. However, here's some things that are typically said. So to build, if it's an average performing PC, you can maybe save some money with everyday prices being competitive with that of PC manufacturers. There's lots of parts that you can get. You can also ensure that which industrial standard equipment or your own choice of what you think is best for equipment from particular manufacturers. OEM stands for original equipment manufacturers, and you get to choose which one you like. Dell, for example, might put together a bunch of different pieces from different vendors, and you may not like that choice. Learning is fun, and so you may do it just even if it's not the best cost-benefit ratio. You're doing it just for your own edification. And then control, you design the control. It's nice to be in charge of what goes where with your own choices. You can take pride in that. Or you just like to control things. Both the initial and required fixes or upgrades, you can control that whole evolution of your machine if you choose to upgrade it, which is not something people typically do nowadays, but it used to be long ago. You'd buy for the potential to upgrade. Now you don't really do that. We used to always pick a machine with a motherboard with a socket that you could put a new CPU in, or more RAM slots, more slots to put other boards in. You still want some of that, but it's not, you don't typically design for expansion. By the time you want to upgrade now, the entire system is obsolete. For buying, if it's a high performance PC, then they'll most likely use good OEM parts, and they can probably do it cheaper than you can because they're buying things in bulk. The learning curve is not as steep. It's just a turnkey system, which means you just put in the key and turn it. That's what that saying means, and you don't have to do anything, so there's really not much to learn. I mean, there's always a little initial setup, but it's minimal these days with all the plug and play. And also very important, if you buy it, you have a warranty that's not violated. If you start trying to fix it yourself, and you also don't have to try to fix it yourself because you can just call them up, and typically you get hardware and software together. So for a while you can just call wherever you bought it from, assuming it's a reputable source, big company with reputation. Then It's just one stop shop, and you call them up, say it's broken, fix it, please. And they won't say, well, is it hardware or software? You know, what the hardware people tend to like to blame the software people, and vice versa if you're piecing things together. So now next we want to consider these different things. Now these are all actually things you consider concurrently, but you got to have some kind of order. Nowadays, most everybody starts with their graphics board. I didn't put that first here just because traditionally you pick your CPU and RAM and your motherboard. But we all know that graphics is dominating everybody's desires these days for streaming video and virtual reality and gaming. We use our computer now like a TV. We do simulations, we multitask, and so with graphics and streaming, everything. So the video card, which is now becoming somewhat of a supercomputer on a card, the old array processors, and, you know, a lot of the architecture we'll talk about from supercomputers 25 years ago, like what I worked on IBM, is now on the motherboards. And you can use the motherboard actually to do advanced artificial intelligence now applications because of that. But anyway, let's start with the beginning. So CPU, we do look at the RAM, look at the board, then the drives, the disk drives. That's the external storage of the computer. When we talk about memory, storage is actually a different than other kinds of memory. So your disk drives, your optical, magnetic, or flash, solid state drives, they're all storage. And then other specialty boards for various applications. And then power, this is something that I have a little piece of a course that I taught on power at Purdue University when I was a professor there, made by others. That's typically how it was done at the huge university. They, somebody wrote a book on this and then made things that we taught from. And this particular person's work was just on power. And it's not a trivial thing to provide clean power. You would want, in a large scale system, if you're the chief information officer setting up a raised floor computer room, to consult a professional engineer who has expertise just in power, typically electrical engineer with a licensed professional engineer with expertise just in power. So move on here.
Interjecting here, I misspoke for a second there. I was saying the CPU or the motherboard is used now for supercomputer type things and AI things, and the CUDA cores. That's the graphics board. That's what I meant to say there.
Although very often now people will look for a graphics card capabilities before picking the CPU. It traditionally has been that you want to pick the CPU first. And now we deal with multiple cores as a standard. And you don't want to always assume you're going to have double, triple, 12 times the speed with 12 times the core, because you have interprocessor communication. And this is a shared memory system. So with caches, levels of caches, and a cache coherency you have to worry about. However, some of that has been overcome, and we read a paper and typically in these kind of courses about ways to overcome the lack of scalability for multiple cores sharing a memory. We also want to consider caches and the cache sizes. The caches, they'll be L1, L2, and you want to consider how much size the cache has. In this course, or the lower level courses, we don't talk about designing caches, but there's optimal sizes for the caches, the number of slots in the cache, and cache blocks that fit into the slot, how much you grab at a given time. if you grab a chunk, cache, if you typically, because of spatial locality of reference, you want to grab a chunk of what could be instructions in an instruction loop, because in all probability you're going to use the next sequential instruction in memory to execute. If it's data, you want to get a big chunk, because in all probability you're going to use sequential data elements in an array. We talk about it in that cache lecture. There's buses to the bus for communication between elements, and it's called a backside bus, which you probably haven't heard of before, but that's just the communication channels within the processor in the chip package, unlike the front side bus, which connects the CPU chip package to main memory on the motherboard, which is a common acronym, FSB. You also want to consider cooling requirements, especially nowadays where people may want to overclock their processors, which is not advisable. But if you wish to do that, people can add extra cooling, even liquid cooling, which if you've heard the lecture on transistors in here, they tend to, the higher speeds back in the olden days with the bipolar transistors would run really hot, need liquid cooling on the large scale systems. And one of the big reasons switching to CMOS, like we did inside of IBM in the 1990s when I worked there, was in large part due to the demands by customers for less cooling requirements for the machines. In PCs, this was never really an issue. People don't typically liquid cool their PCs, but nowadays some people do, especially, as I mentioned, if you're going to overclock.
One interjection here, if we just remember that we have SMP, which stands for symmetric multiprocessing, also used to mean shared memory processing, is still, and probably for the foreseeable future, still will be the standard for PCs. Although MPP is on the horizon, almost all supercomputers have gone that way. That's massively parallel processing, where we're not doing a shared memory. Every processor, every core is the same as processor, has its own cache and its own memory. And then there's some kind of dynamic or static interconnect architecture that makes all that work. So somewhere on the horizon, I've yet to see a PC with an MPP architecture, but possibly in the future. For now, SMP is where we're at for PCs.
Now, continuing on picking our CPU, clock speeds, of course, matter. And as we learned in other lectures, we're pushing the limits here on speed as well as transistor count. You normally don't ask about transistor count. There's billions of transistors now packed in, but we know that there's a limit to how many we can pack in due to Moore's law not really scaling. It's asymptotic. We're going to hit physical limits. We already are now with getting close to an angstrom. Angstroms in size, which is an atomic diameter. You can't get any smaller than atoms. Putting your minimum feature size together, but also clock speeds. We're switching so fast now. The speed of electricity is approximately 1/3 the speed of light, and so there's limits to how fast we can go. Now we're putting, we have multiple cores, of course, now, which are helping with performance. So we want to talk about clock speeds. When you're purchasing, you still want the fast as possible. And you want to keep in mind that the CPU, the fastest thing is the fastest thing in the computer and the PC, faster than the motherboard and the RAM. In the past, you did have to consider that when purchasing, that the speeds are a mismatch. And even called Intel once in 1989, I guess it was, asking about picking proper processor speeds to match up with motherboard and RAM. And what it ended up being is you want a common denominator. Like back then it was like a 120 megahertz processor and a 90 megahertz section access time, which is 1 over speed, but RAM and a 60 megahertz process or a motherboard. And so they had a common denominator of 30, they could be divided by 30. And the Intel engineer said that's important in the finite state machine and the control unit that's dealing with RAM and RAM accesses across the motherboard, that you don't have wait states in the finite state machine driving the control unit. And so nowadays that's done for you. In the most part, you don't. I haven't heard people thinking about that, but it's just good to know that there are different clock speeds. There's, the fastest thing is the CPU, and the other things are slower. Now, we only talk about Intel and AMD now. Apple used to have Motorola processors in the 6800 in the olden days, or 68,000. And then when I was in IBM, I've told a story about how we developed the PowerPC chip actually to help Apple, ironically, and Motorola compete in the marketplace, just to keep the market alive. There's a long story I tell about that, how it was funded by DRAMs, and then dumping in the DRAM market caused lack of funding for the PowerPC chip. And so IBM was doing it below cost, and it was really just to keep the markets alive, believe it or not. So IBM was 450,000 people at the time, and all PCs were done by other companies at that time in the mid 1990s, even though IBM, dominated the PC market in the 1980s, even though it was never more than 10% of their revenue. Because it was considered a junk machine with other people's parts. The large-scale $1 million machines I worked on and the other systems that are inside IBM are all with IBM processors designed inside of IBM. Our System 390s, motherboards, the whole cage, RAM, everything, actually the operating system and the applications were all developed inside of IBM for $1 million machines. But so nevertheless, Intel now dominates these Wintel Windows operating system Intel machines, and it's essentially the same. It's the same instruction set of machine code that all the high-level language gets compiled down into, and the assembler gets assembled into. So it's all the same family. Now we talk in other lectures about microcontrollers, which Intel and Motorola both have families there. That's different. But so there's only really one microprocessor instruction set we're talking about, but you do have a choice of AMD or Intel, and they are competing against each other and dealing with fabrication facilities and global supply chain shortages at certain times, according to 2020 during the COVID. But the underlying architecture also would be different too, so as well as the minimum feature size, depending on the foundry where they're developing their chips. Also, when you're purchasing, you don't want to buy the bleeding edge of really anything. It goes for buying a brand new car, whatever. You're going to pay a marginal price for that last couple months of being the hottest thing on the market. You just wait 6 months, let somebody else pay for the brand new thing. You pay a lot cheaper, relatively speaking, per unit time. 64-bit processing. Now this is a given now. I was working in an IBM on some of the very beginnings of this, where we first started putting 64-bit processing in anything before anybody else. But there's good things to know for anybody about this, even though it's a given now, is there's difference between data and addressing. In data, you want as big as possible. And the graphics cards do much more. So we're bigger than 64 bits. So a graphics card processing everything in there, because there's huge chunks for multimedia processing. And so the bigger, the better with data. However, with address space, you're talking about address lines, and the number of address lines is 2 to the power of whatever number you're talking about. So if 2 to the 64, if you wanted 64-bit address space, that is 16 billion, which is ridiculous, right? So 16 gig times a billion. So that the physical memory does not, you don't need that much. The reality is you have typically 40 pins coming out of the back of the CPU, and 2 to the 40 equals a terabyte of RAM. And we were still not getting close to that, but it's, we're talking about RAM now, not storage, not hard drives, optical or magnetic or solid state hard drives. We're talking about actually dynamic RAM in a PC now, we're talking about. And so we're still limited to 40 pins. Now, large scale systems, $1 million systems, go more than that. But in a PC, nobody's exceeding a terabyte of RAM. And I update these lectures. I've been teaching this course for 23 years, and I have had to change things. So I'm updating the whole thing right now, but we're not at terabyte scale yet for RAM. So typically only 40 address pins coming out of the CPU chip package. So you want to pick your RAM also and your motherboard at the same time. There were times in the past where you didn't do that, but now you certainly want to do that most of the time. And the front side bus speed needs to match, of course, for everything to coordinate, as we mentioned previously. RAM stands for random access memory, as opposed to ROM, which is read-only memory. And it's used as main memory. We've talked about this before. Main memory. When you speak of memory, you're typically talking of the dynamic RAM of memory. You're not talking about the registers or the stack or the caches, which are all static RAM. And you're not talking about the storage, which is the magnetic or optical or solid state storage. Dual, DIMMs are just dual inline memory modules, just how they plug in, both rows of connectors. And it is dynamic, so it's volatile and needs to be refreshed. It won't hold what's in there unless it's electronically refreshed. And there's a number of variations here. Here, just some typical ones is DDR, double data rate, using both positive and negative clock edges. So in this course, may not have talked about it yet, but the digital waves versus the analog waves, and a digital wave is a square wave, which with a leading rising edge of the pulse and a trailing edge of the pulse, and a falling, rising and falling edges, and use both positive and negative clock edges in double data rate. DPRAM is dual ported RAM, allows multiple reads or writes at nearly the same time. And there's a number of variations, and there's a link you can click on the bottom to see. This is just the basic ideas here. Also, motherboard may have dual channel capability to allow 2 banks of RAM to work concurrently. And then now caches use static RAM. Static RAM is also volatile. It does not need to be refreshed, though. It will hold with the electrical, just everything's powered up, it'll just hold. It doesn't need to be refreshed periodically. Now it's faster, less dense, and more expensive. So this is why you don't have all of your memory made of static RAM. You can't afford it. It's also why you don't pack all of your memory onto a single chip unless you're a microcontroller. You don't need that much memory. It's because it's too expensive and not dense enough to warrant packing it in on the processor or making all of your memory out of static RAM.
I won't click on this link here, but if you're watching this on YouTube, there'll be a PDF in the comments that you can go into and click on it.
Now we're going to talk about the motherboard, where the CPU and RAM are connected. There's a front side bus connecting channels, pathways of the bus. The backside bus is in the CPU connecting everything. The front side bus connects the CPU and RAM. The CPU processor needs to plug into a socket, and you got to make sure you got the right socket on the board for whatever processor you're going to use. Then there's a chipset. In addition to the bus communication pathways, you have a chipset, which originally was up to 60 different chips back many decades ago. In the beginning of the PCs, it was a number of different chips on a motherboard. Controlling things. So you can think of it as bus controller in general, but there's lots of things that need to be coordinated. It broke into a North Bridge and South Bridge for the past couple of decades. There's different ways of doing this, but just know that there is a chipset, a number of chips that control what's going on, and then the bus itself, the pathways, referred to as a bus that everything connects to. Continuing talking about the motherboard, you want to make sure that motherboard has dual channel capability. If you're going to do the double channel, you want to make sure you can handle your graphics card. So NVIDIA, Crossfire, whatever graphics card now dominates typically what you're purchasing. Most people for multimedia, gaming, streaming, video. There are a number of sockets here you see are slots. The ISA, you're going to have a hard time even finding that on anything. You may want to make sure that if your client or people in your company have certain specialty boards. We had this happen in the college here where somebody had something built for several $1,000s just for the ISA slot, a special material sampling, computing experimental setup, custom built. And then computers upgraded, the ISA slots went out of fashion or out of obsolete, but we need to maintain the board, so needed a special box just to translate, and then something connected into one of these other slots, a PCI slot. So the PCI is for more recent, not super recent. And then the accelerated graphics port was something that was just for the semi-recent ones. I mean, it's decades old now, or decade old, but that was something just to accelerate graphics. However, as you see below here now, the whole new thing is PCI Express. And this is a whole paradigm shift here from doing things in parallel. They kind of look the same, but what you have is multiple serial lines. So parallel is when you have a bunch of things next to each other happening, all the bits coming in. Serial is where you stack your bits and you put them in a line and push them through the pipe one at a time. And then, that you wouldn't think that would be faster to do that, especially if you need to packetize it. So in packets, like in networks, you put a bunch of other information we'll look at in a second. So you would never have guessed this 30 years ago that anybody would try to do serial communication at this level, because that was just for the networks and the computers to talk to each other, but it was never as fast as on the board. But now things have gotten so fast and serial communication has gotten so sophisticated that you can do things in serial very fast. So that's a very important thing here. This PCI Express uses a packetized serial is the most important part, but the packetizing just makes it even more amazing that it can work. Protocol it's like that used for Ethernet, TCP IP packages. Here is an example of network protocol TCP IP. Certainly don't look at the details here, but just realize there's a lot of overhead when you make a packet. And so this is not the actual packet that's used inside the computer, but just to give you an idea of the overhead, you see down the bottom, there is the data, and everything else there is overhead for error correction and communication, just for beginning and ending, beginning delimiter, a number of things. And so, again, you don't want to look at this too much. It's just for reference. And this slide also, here's the details that if you want to know more about the networking, this is the beginning of that. So you can take a look at that. Continuing on the motherboard, now we do everything in Rom Bias, which is when you start up, you just go into the Rom Bias, and it's a software kind of thing. But in the olden days, not too long ago, you used to physically configure the board with these wire connectors. You can still do this on custom boards for robots and such. And but what you would do is there are pins sticking up on the board, big spiky pins sticking up, conductors, and you put these little jumpers, little plastic black little things that go and connect the two. So you slide them over to two of them, and that connects the two together. And that's how you would configure for your CPU frequency, your front side bus frequency, your CPU voltage. Remember that different technologies have different voltages, as I mentioned. Typically 3.5 for CMOS and 5 volts for bipolar TTL. Now everything's plug and play, so there's auto detect most of the time for this. You also have your disk drive connectors for your storage. Right? You have IDE pins, that's the older pin sticking up from the motherboard called parallel ATA, serial ATA, which is the newest thing. And that's a little red cable typically from the motherboard. You also have connectors for a RAID array if you want your server, for instance, a bunch of redundant drives. Also on the motherboard is your power connector to connect to your power supply. So you have, we'll talk about power later on. You've got a large amount of voltage, relatively large, coming out of the wall, and you need to transform that down into smaller voltages for this delicate circuitry, different voltages for different technologies, 3 and 3.3, 3.5 for CMOS, 5 volts for TTL bipolar. Well, but 12 volts also, because you need to have more power. Power equals volts times current. And so you need to supply both to turn the motors. You have motors in a disk drive, your disk drive motor and your fan motors. You can't do that very well with lower voltage than 12. So you have that available from your power supply. And you may need even more sophisticated power demands for your cooling system. So the watts, the power rating in watts of your computer is what you're talking about here. Watts equals, power equals volts times current. Watts is power, volts times current, which is amperage, and measured in amperage. We'll learn more about this later.
Small interjection here. The cooling systems may need not just pumps for the liquid to go around, but also condensers. And in refrigerant cycles, you can condense and let expand fluid, refrigerant, to remove heat.
Continuing with the motherboard now, we want to talk about the ports that come off the motherboard. Now, some of these come off of other boards that plug into the slots in the motherboard. So this is essentially the back of the case of the computer. But we're talking mainly about the motherboard here. And so there's a number of different things. Now, you're not going to find all of these things on any given computer, but you want to just get to know a little bit about them. So USB is Universal Serial Bus. This was a brand new thing, seemingly recently. I guess it's been many years now, but This was an idea of putting a lot of different types of communication into one thing, one connector, one wire. Greater than 100 peripherals simultaneously, hot insertion and removal. So you used to not be able to just unplug things. Now you still, some devices, Apple's, you need to eject your thumb drives, you're supposed to. But the idea with USB was just whenever you want to plug it in and out, it's not going to hurt anything. Your serial ATA, we talked about before, for storage, you can have external drives. Your SCSI is for multiple exterior hard drives. Again, maybe a server. Firewire was an Apple development for cameras and portable storage. Actually, it was one of the very first things for multiplexing. You may use several tasks on one wire. You have your network jacks. Your network jacks allow you to plug to your network, your local area network, like in college, a wired connection, not the wireless. Dial-up phone jack is somewhat of an old thing where you had a telephone, a wired connection, and your modem would talk through the telephone line. When you had a telephone plugged into the wall, you probably don't even remember that. That's called a landline. It wasn't called that in the old days because it was the only kind of phone that there was. But now, to differentiate from the cell phones and the wireless, it's called a landline. You can still get them. Then you have a number of other jacks. Some of these coming off the graphics boards for connecting to your monitors and other digital devices. So in the next lecture, I'll ask you to drill down into some of these, take the time and to click on some links and learn about each of them. Right now, we're just going over these. So we have other digital video kind of interface, sound things, audio jacks, combined audio and video, your HDMI, of these, of course, in the back of your TVs now. And then a couple more here on the next slide. Actually, this file has been now split in two for audio production. It makes a pretty large file. Going to the second one. First thing. First thing we want to speak of here is the Rom Bias Chip. You probably know of the Rom Bias is something that you go into in your software when you're starting up, and you can configure things in there on startup of your computer if you choose to. But it is actually a hardware thing that's going on here. And so what the computer is doing is two main things. Well, first of all, it's a read-only memory as opposed to RAM, but it's actually writable since it's in a flash memory, accessible through the CMOS setup during your boot up. Now, the two main things that happen in the BIOS, this is what I want you to know most, is post and loading the operating system and starting it. So post is power on self-test. And there's a number of things. Maybe I'll ask you to name a couple of them. So you're verifying the integrity of the BIOS code itself that's written in there. You're trying to figure out, the computer's trying to figure out why is this even starting up, what's going on here. Then more importantly, really, is finding, sizing, and verifying the system main memory and cataloging the devices and buses and making a map of how everything works so it can begin to coordinate all that. And then provide a user interface for system configuration, identify, organize, select devices available for booting, construct system environments requiring by target OS. So I might ask you to write a little paragraph or a couple sentences about post. I wouldn't ask you to memorize all 7 things, but you should know that two major things, post, and the second thing, loading the operating system from the disk. This is what the BIOS does, loading it up, loading it from storage, the disk drive, into RAM, main memory, and then start it executing. With two things going on there, but it's this one second step. So post is the first thing, and then B is loading and starting the operating system. We also want to talk a little bit about the clocks. There's a quartz crystal, a little sliced piece of quartz that there's a little rock inside of a device, a tiny little device where you put electricity in it, and it vibrates at a fixed frequency and outputs clock frequency. And all the clocks are derived from this main clock. Your CPU, RAM, and front side bus, but also the things that stick into your slots on the motherboard, the graphics board, and other boards you may have using the PCI or AGP or ISA or PCI Express, whatever slots, also your ports or USB ports. Everything communicates to some function of this, derived from this main clock. You can overclock too if you want to risk it, and it's a risky thing to do. Your devices are made to run at a certain speed under certain temperatures. You could try do extra cooling and overclocking if you want, or just overclock a little bit, but it's risky. You can burn your devices out. Next is a DMA, direct memory access. This is a special little chip that allows you to communicate directly with input-output from your RAM. You don't need the processor involved. The CPU gets freed up, and this little device allows the RAM to talk directly to I/O, so you can dump things in and out of RAM onto the I/O and vice versa. Then you have a battery that is made for just maintaining the main date and time, real-time date and time, and it looks like a little watch battery on motherboard. These next couple slides are some random internet boards of the past that you might want to take a look at, and just get familiar and ask yourself, how recent is this? None of these are that recent, so that would answer that, but they're not decades and decades old. You see PCI Express in there, that's newer than the ISA, and you see the slots on there, and it's number 6, 7, and 8. That's more recent than the ISA or PCI slots or the AGP. Serial ATA, see that. A couple little things tell you it's not super old. Here's another one. You see HDMI, which is pretty recent. You can date things by the USB numbers also. Just your DDR3, there's actually 4 now. So you can get some idea of the time. But all these things around the perimeter, some of them may be a little obscure references sometimes, but when people put up their picture like this. Like a debug LED, that's not a typical thing you see here on this one. But just get familiar. This should not be foreign for you to look at this. Ask yourself what's plugging in where, and you'll see in a second here where I ask you to drill down into some of these things. Here's another one. You can just look around outside and see if there's anything that gives you a hint of what's going on time-wise. And another one. So just look around, and look at the slots. And if you see an ISA slot, that's an ancient board. You don't see that out here. You still see PCIs and AGPs. You also need to consider whether or not everything you are putting into the computer case will fit in the case itself. Most typically, it's going to be an ATX form factor. The form factor is the specification for the dimensions of the box and the layout.
Interject that ATX is the most common. I won't click on that there, but it's the way things are laid out for energy efficiency and also just for fitting things in without putting new cards in and out. Also for cooling, with separation between things. So that layout, the physical layout of things, with ATX being the most common.
Now we're going to have entire lectures on a number of other things, on two separate lectures, one on graphics boards and one just on monitors. We also have talking about storage and drives, specialty boards, all separate topics. And then providing clean power, that's certainly something that you want to, especially if you're doing on a large scale for a computer room race floor, a big corporation. And I did this for several companies in Texas and California when I was in the building industry. So it got me into high tech. One of the reasons. And so it's not a trivial thing. It's not just a simple power strip backup. There's a number of very scientific engineering things to talk about. I actually taught a whole course of this at Purdue University. I was a professor there. They mixed it with controls. Now, before I ask you to spend some time learning about all the different things that can plug into your computer box case, a couple main principles. I want to wrap up here. A basic principle is as the number of transistors that fit on a chip increases, the number of chips on a board goes down. And this is good for a number of reasons. If you've ever done breadboarding or wire wrapping or made a printed circuit board or soldered anything, the soldering can be problematic. You can burn up things. You can, a number of problems. There's less chance of, if you have less chips on the board, less chance of stray capacitance or inductance. We'll talk a little bit about electrical power coming up. The engineers know this from physics and analog circuits, what capacitance and inductance are. So you can get, unintentional capacitance and inductance messing with your electrical pathways and wires and channels on the printed circuit board, the PCB. If you have less distance between the components, it's a good thing for less chips because they're therefore faster communication speeds and less chance of signal degradation. Seems like a short distance, but you're talking about things trying to happen essentially close to the speed of light with electricity moving that fast across certain distances, approximately that fast. Speed of electricity is in copper, for example, is about a third the speed of light. So same order of magnitude and cheaper. For less things put on there that you need, then it's cheaper. Now, on the horizon. So this is also a very important principle on the horizon, what's coming up and already happening somewhat now. We'll talk about some of this a little bit in this course and a lot more in other courses. 3D silicon circuits with all the caches, RAM, chipset, DMA, graphics, everything, communication on a single chip, kind of like a microcontroller as we talked about, but all the complexity on a single chip because you can really pack it in now. Or even on a wafer, like a whole, people have done this, Hitachi's done this, a whole wafer size, big 8-inch or 6-inch disc size piece of silicon, right? You can do that. There's complications to doing it. Or a cube, that's even more complicated because then you're talking about routing wires through the big mass. Not just on the surface, have several layers on the surface like you do VLSI circuits now. You have several layers and then some overhead channels and vias dropping down like overhead busways or channel pathways. But a cube, now you've got some real routing issues to sort out to get everything connected. And you also have problem with thermodynamics because the thing is going to heat up quite a bit internally. And so how do you cool that? Another thing you could do is super cool everything. You know, that's down to absolute zero. Of course, you need a controlled environment and special setup to do that. It's going to be a little costly, but if you're going to want a little more speed, that's free of the thermodynamic constraints, you might do that. Neural network circuits. Now, I do give whole lectures, big parts of robotics and machine intelligence course I teach. Parts of other courses are neural networks. Developed, invented, created 2 neural network chips in the early 1990s. One was my master's thesis that I put a patent disclosure document on. Another one you can see hanging on the wall in the lab, which is beginning research and PhD research before I got into robotics. And I've published some papers and things since then, even drafts of a book chapter I hope to write. Now, that was all theoretical kind of stuff 30 years ago. Now you're going to find it. You find it, and we're going to talk about it even in the processors now, in the PCs, there's neural networks. And how do they work? We'll talk about that. Network type CPU multi-core architecture that actually speed up with more cores. So I mentioned that earlier in the last lecture, that the problem of scalability and Amdahl's law and the law of diminishing marginal returns when you're trying to share a bunch of CPUs trying to share one memory, and the SMP, symmetric multiprocessing, shared memory processing architecture, you can scale only so much because of interprocessor communication delays and the problem of parsing problems into chunks that make sense to spread over a number of CPUs and then synchronize later. That was a problem that's now potentially being overcome by treating all the processors as network nodes. And if you can get the routing algorithm to work, which is not a trivial thing, and it's still not mainstream to do this kind of thing. But if you can do that, you can speed up, just like you can speed up the internet or traffic flow through a city if you have more intersections, spread out the traffic. Also, next, pack it all in a small box, like the back of the monitor. That's already here, isn't it? So you see that now in tablets and Apple computers, and they're not less fast, right? It used to be when you did something very thin, you squish it in there, and then there's a performance hit you have to take. So we can get small now and still be powerful. One universal connector for everything. That's next. Like a super USB, just one cable for everything. We're not there yet. I still want you to learn all these different things that can connect. For one thing, you just got to learn there's many different ways that things need to communicate. Just because you make some wire and device that allows all of them to happen simultaneously doesn't change the different communication protocols. So you should learn that. And then lastly, super small external portable storage. I mean, we're already getting there with flash drives, terabyte size. And so that's a whole new revolution, recent revolution. Before we begin our exercise, where I want you to drill down into all the different connectors and ports to the computer case. Just think of some future networks, a little bit science fiction, but maybe not so much. A lot of the things people just imagined long ago have become reality. So maybe we will live inside the network, or it will live inside us. We're not far off from that, right? We're always connected now. Network, you're staring at your phone all the time. All of us are. We can't get disconnected sometimes, even if we want to. Or it will live inside of us. Elon Musk saw his Neuralink, that whole new initiative and company he started up amongst all of his very creative companies, tapping directly into your brain. So you can upload, download information. It's just in the infancy stage, but it's here. It's starting. Next, we do want to talk more about this: virtual and augmented realities replacing real physical experiences. So we already have virtual reality happening in the lab here. I have architecture students digitizing with some very sophisticated rendering software, buildings on campus and other buildings, new buildings, and putting it in virtual reality. And then walking around inside, it's quite an experience. And then augmented reality, which is a hybrid where you're still, like, for example, you're dealing with a real, like you're looking at something real, like maybe an engine. You open your hood, you look at your engine, and then you're wearing special glasses that bring up a schematic that lets you see essentially the inside as an overlay of what's going on in the engine. And it's also, in addition, the augmented reality allow you to connect to other people. So you could supervise, a worker doing something, in a remote spot where you are not at, or a number of different workers, and then you just kind of tap in and you see through their eyes what's going on, and you load a schematic to help them, and you could talk them through it, and you could be in multiple places. A lot of telemedicine, especially nowadays, where there's a need for more doctors maybe than we have at the moment. In certain crises that can happen, it'd be good to have telemedicine allow augmented reality in a real way. So it's almost like hands-on, with the added benefit of being isolated from a potentially maybe contagious disease. So, virtual and augmented realities replacing real physical experiences. Now, seems like we're on the verge of that. The next thing, hopefully we're not on the verge of, is the Matrix, where we are being faked. People believe they're in reality and you're actually in a simulation to control your mind. That would not be so good. Although with deep fakes and everything that we're immersed in during elections, where we think we're having free choice, and we think we're seeing the real thing, maybe we're not. So beware of that. The Borg, we definitely hope that happens. That's a Star Trek Next Generation reference, if anybody's still a fan of that. All science techie people for many decades until recently were almost all inspired by Star Trek. It's not quite so relevant anymore, but the Borg were these cybernetic organisms, humans with implants, and they're all networked together, and they had enhanced features, vision and communication, certainly, and even strength. And one arm had tools. The wrist, your hand was cut off at the wrist, and you put different tools on. And then they wanted to assimilate everybody. So they thought they were so advanced that they decided humans or other species of Vulcans and Klingons and everybody else should be assimilated. And so resistance was futile was their motto, and they tried to destroy the earth, and that was a whole big episode. You have to see that. So, we don't want that. We do like to have prosthetics. If you lost a limb or something, then you do want to assist the disabled, certainly. But we don't want to go so far to have these cybernetic organisms think that they are better than everybody else and try to destroy the rest of us. That's not so good. Surrogates, that's another thing that could become real, where some cybernetic, some robot is living out your parts of your life, and you are experiencing what the robot is physically experiencing by just being in a virtual reality. And then in essence, the surrogate is like an avatar simulation, except in this case, the avatar is in the real world and you are in virtual space and living vicariously through that robot. There's a movie called Surrogates you can watch for that. Okay, now on the next 3 slides, as an exercise, I'd like to spend somewhere between 30 and 60 minutes and click on each of the links. For some reason, one of the links is broken. Just copy and paste that into Google and go find whatever is recent. Links will break over time, of course, but this information is still relevant. I would like you to just drill down and look and ask yourself, what are all these connections? Answer that to your own satisfaction. Some of them may be obsolete, and then it's like, well, that was a nice footnote in history. At least you know it existed. You should know history. You should know history. So this is broken into 3 parts here. the slide you had seen in the previous lecture. Here's a bunch of other connectors here. Learn what all these are one at a time, go through. And then lastly, this slide. So spend on these 3 slides and all these links at least 30 minutes, right? And then hopefully up to an hour, not much more an hour, just know basically what each of them are.
You can consider that an unstated homework for the moment. I might actually make that a hand-in homework soon.
Watch this 9-minute video about best motherboards for gaming in 2021 and think about how each of these are similar or different from what you've seen in this lecture.
Okay, let's do this, and this will be the end. Take us right to the end of our time period.
This flashlight can burn through anything. Cardboard, plastic. The motherboard performs the function of a spine in a computer system, and it supports all the components in the system. Motherboards were not used to be so popular a decade ago, but the latest inventions and technologies resulted in a huge spike in the importance of motherboard, and now a motherboard should not only perform well, but look great as well. When it comes to the best gaming motherboards in 2021, there needs to be a lot of refinement because there are a lot of chipsets, let alone the number of motherboards for each chipset. As for the HEDT platform, the latest AMD platform chipset is the TRX 40 chipset, which feels quite unique as it does not follow the conventional chipset names, and it supports the 3rd generation AMD HEDT processors. So, let's have a look at the best gaming motherboards in detail. Links to all the motherboards mentioned in the video are in the description. So for the most up-to-date price, check them out. Starting our list with ASUS ROG Maximus 12 Hero Z490. ASUS ROG Maximus 12 Hero coming at number 1st is a worthy contender for Best Gaming Motherboard 2021. Where you ask for elegance or for a powerful performance, Maximus Hero 12 has both to offer. Intel with its Maximus motherboards lineup has brought rich features, amazing aesthetics, top-notch performance, exceptional overclocking speed to the gaming industry. The ASUS ROG Maximus 12 Hero has an exemplary high-end and feature-rich Z490 board. The Maximus Hero 12 features integrated I/O shield, 5 GB per second land speed, enough room for memory storage, Wi-Fi 6 and SLI, scalable link interface. Top-tier memory overclocking, as it reaches 4000 MHz CL16 stable with a Trident Z Neo kit. For CPU overclocking, Maximus Hero is able to achieve 5.2 GHz on all the cores. ASUS never disappoints with its design. May it be their high-end gaming laptop or any other gaming-related accessories, you would witness enough elegance and attraction, especially with an amazing RGB lighting implementation. ASUS ROG Maximus 12 Hero comes with relatively a compact form factor and radiates grace. You also get AI networking with Wi-Fi 6 support and ASUS Aura Sync illumination, which makes it the best choice you should consider while upgrading to a 10th generation Intel Core processor. The only area where this best Z390 motherboard suffers is that tackling the heat production when fitted with some powerful processor like the latest 10th generation Intel Core i9 to 10900K ASUS has worked hard to resolve the issue with VRM thermals, voltage regular module, that barely exceeds 60 degrees centigrade when introduced to high performance. At number 2, it's Gigabyte X299X Aris Designer. The Gigabyte X299X Aris Designer stands at 2nd place on the list of Best Motherboard 2021 for gaming. With its high-end features and brilliant design, the Gigabyte X299X is made solely for the 48 lanes of Extreme Intel 10th generation. The X299X Designer 10G is equipped with loaded Intel X550 dual 10 GB per second Ethernet and 2 Thunderbolt headers with DisplayPort pass-through on Intel's 40 GB per second controller. A 4-drive expander M2 card and Wi-Fi 6 with 2.4 GB per second speed finish a feature set of which the motherboard perfectly balances the price efficiency. Gigabyte X299X Aris Designer comes with a good-looking design, a compact, but packs enough on its deck to bring the best gaming experience. The 2x RGB lighting extension, 1x noise sensor. The kit involves 2x thermistors for heating purpose and packs 6x SATA slots. Similarly, the X299X Designer holds a G connector bundle for front panel button LED cable ends, 2 Velcro cable ties, and a dual-band Wi-Fi antenna. Gigabyte X299X Aris Designer offers an easy tune feature, which makes it
Pause that for a second. This is text to speech. It's designer, not designer. Wi-Fi, not Wi-Fi. And SATA connections, not SATA. Some other things.
easy to adjust the processor's frequency and levels of voltage. The RGB Fusion 2.0 feature of Aris Designer processes controllers of the RGB on motherboard and graphics card. X299X Designer 10G holds enough primary, secondary, and tertiary latency, giving you an edge when it comes to modular programming. X299X with its DDR4 to 3600 settings, its memory bandwidth beats the past Asrock's X299 Taichi CLX. At number 3, it's MSI MPG Z390. In case if you are looking for a motherboard that has comparatively a small form factor to fit in everywhere by not asking for much space, and still claims to be the best amongst all the micro Atx Form Factor, MSI MPG Z390M Gaming Edge AC packs enough high-end gaming features at a bit more price. MSI MPG Z390M offers USLI and crossfire assistance, as well as 2 XM2 slots, along with everything that takes gaming to some next level. If you are specifically looking for a small-sized motherboard with high-end features too, you must consider MSI MPG Z390 as your best gaming motherboard 2021. MSI MPG Z390M helps the DIY users with its compact design and boosting your system to the next level with its amazing tuning and troubleshooting features. MSI MPG Z390M is really easy and simple to fit in your system without any complexity or rocket science. The well-built-in
This will take a second. Say some things here. This is pretty recent. This was last spring. I haven't uploaded a new one for 2022. I'm going to do that for a homework assignment. You may have as a project to design a gaming PC, although I'm rethinking different things you may do. I like to change it all the time. But gaming is still relevant for most all of us. Let's go, computer. Time out here for the class. Give it another second. Let's see, high definition. Maybe if I turn down the resolution some.
side circuit system helps the motherboard to deliver power and efficiency. High-quality materials and intelligent optimization of fans help to cool all necessary components, which is critical to ensure that the system is always stable and delivering the best performance. Most of the MSI motherboards are made with great audio and the latest LAN networking capabilities that bring immersive gaming. At number 4, it's Asrock H370m Pro 4. If you are willing to have a best gaming motherboard 2021 within a limited price range and even not compromising on the key features, you must go for Asrock H370m Pro 4 gaming motherboard. Asrock H370m Pro 4 diverges the high-speed I0 channel between the 2x USB 3.0 ports and 2 SATA headers. You will definitely love the port combination of Asrock H370m Pro 4, that too in an affordable price tag when compared to the competitors. To make the H370m Pro 4 more power and performance efficient, Asrock, despite using the microstrip, they have used stripline routing with plane on outer layers that make use of 4 layers. Best gaming motherboards sometimes suffer to bring power via power chocks, but Asrock H370m Pro 4 with its 45A checks all the boxes to bring enough for delivering electricity to the processor for enhanced and optimal performance, keeping the temperature as low as possible. The PCB fabric glass with tough tightness design helps to minimize the space between the PCB layers, keeping the motherboard safe from short circuits that are caused mostly by humidity. H370m Pro 4 being the best motherboard 2021 when it comes to throughput performance, extremely moderate processor utilization, increased stability, making it quite able to bring you the best network experience. Asrock H370m Pro 4 can be considered amongst the top motherboards of the time. At number 5, it's Asrock X570 Phantom. If you are thinking of setting up an AMD setup for the PC you are building, then you can't ignore the Asrock X570 Phantom Gaming X570. Phantom Gaming X has everything that comes in a best gaming motherboard 2021. Whether you ask for compact, good-looking design to settle easy, not holding much of a space, one of the best gaming features to bring optimal gaming experience, the high-end cooling features to tackle heating issues when introduced to intensive situations. The best between competitors with its Wi-Fi 6 feature to boot. Asrock X570 Phantom Gaming X carries a limitation of upgradation. You cannot make any upgradation keeping its physical design in perspective, but professional geeks shouldn't be worried about this board when it comes to performance. You won't witness any other limitation or weakness in this best motherboard for gaming. Asrock X570 Phantom Gaming X comes with one of the best form factor, carrying enough powerful port combination on its deck to offer lightning-fast data transferring. There is a peripheral component interconnect Express 4.0 M2 SSDs, which can transfer with twice what was offered previously by third-generation ports. To provide trouble-free power to the processor, X570 holds excellent overclocking potential, keeping the temperature balanced. To know whether the boot DRAM VGA CPU working fine, Asrock X570 comes up with vital troubleshooting mechanisms that also makes it easy to recognize the main problem. To make the signals more stable and the powerful graphics card to firmly hold by the PSI slot, Asrock provides 2x USB 3.2 Generation 2 ports will let you have an extra fast file transferring experience, with transfer rate up to 10 GB per second. Detecting and resolving single-bit errors is no more a difficult job when you have equipped error-correcting code. You have the opportunity to make wireless connections via M2 800 1.11 AC slot. Asrock X570 heating of the chipset and MOSFET is tackled by the extra-large aluminum alloy to let the whole system work stable.
At Aspen Dental, we're a different kind of dentistry. When new patients get a complete exam and x-rays free without insurance.
Hello and welcome. If you're planning on building your